just in case it isn't fresh in your memory. Okay, so last week we did start on hyperbolic PDEs. These are perhaps the most plentiful, most commonly used in modeling problems, and they can be a bit thorny. Okay, they're not as straightforward as elliptic PDEs to solve. Okay, so I'm just going to recap what we looked at last week. Okay, in this chapter we're looking at solving just this equation. Okay, this is the advection equation. It's the simplest form of a hyperbolic PDE. Well, it's the simplest one. It's quite useful. The reason why it's useful is the fact it's hyperbolic. Okay, so it has all the properties of more complicated hyperbolic equations, such that it can include discontinuities in the solution, which elliptic and parabolic equations can't. But also, it's very easy to find the exact solution. So we tend to use this advection equation here as a test. Okay, so we want to derive finite difference schemes, but quite often we might have a complicated system and we're not sure whether the finite difference schemes will work. Well, what we do is we test it against this simpler one. If they don't work on the simple one, they're not going to work on the more complicated ones. So it allows us to sort of discard any schemes which are no good. Okay, so this is the simplest one. If the initial conditions of that function, then the solution at time t is x minus vt. This morning I noticed there's a typo in the notes. It says x plus vt. It should say x minus vt. It's usually quite obvious when you try and run it, your solution goes the wrong way. Okay, instead of heading to the right, it heads to the left. Okay, so it's normally quite an obvious mistake if you made it. I made a typo in the note, so it should be x minus vt, not x plus vt. How do we derive finite difference schemes for solving this? Well, as we've been doing so far, we simply replace the derivatives in the equation with finite difference approximations. As simple as that. We rearrange them, and we saw last week how we rearranged it so that we have what we call a time marching scheme. So we can calculate the values at the next time step using values at the current time step. We also looked at this idea. Okay, not all finite difference schemes are stable for the advection equation. What do I mean by that? So I've just got MATLAB here with the program which we looked at last week. Okay, and in this program, I'm using a dt of 0.009. Quite a small time step. Okay, what we're going to be looking at today is why am I using this small time step? But if I increase the time step a bit, let's say 0.02, and what I'm going to do is I'm going to run that problem, and it soon becomes a bit unstable. Okay, that oscillations, that's just instability. So these finite difference schemes aren't stable for all values of delta t or dt. Okay, so what we're going to be looking at today is for what values are these schemes stable for. Okay, and once we've looked at that, we're also going to look at the idea of a few more schemes and look at some second order ones as well. Okay, so this is the advection. Okay, so this is again a recap from last week. Okay, the advection equation just moves a profile or something down a channel. Okay, so let's say this is your red line up here. This is some initial conditions. Okay, so this is your red line. If you apply the advection equation to these initial conditions, what you have over time t is it just moves that triangular shape down a bit. That's all it does. Okay, it doesn't do anything, doesn't introduce dispersion, it doesn't introduce anything which we'd normally associate with modeling of physical systems. All it does is move something from one place to another. It's just simple advection. Okay, we looked at the idea of convergent scheme, okay, using the Lax equivalence theorem. Now, I was sort of halfway through that. I've done one half of the Lax equivalence showing it's convergent. Today, we're going to be looking at the other half. Okay, so what we have is if big U is the actual solution, and our little u is our approximated solution, well, the difference between the actual solution and the approximated solution should tend to 0 as we decrease delta t and delta x. Okay, so as delta t and delta x, which is our steps, our time and spatial steps, as these tend to 0, our approximate solution should get closer and closer to the actual solution. And that's what we want, okay? And that's known as a convergent scheme. We looked at the idea last week about Lack's equivalences theorem, and it basically stated that a scheme is convergent, it must be consistent, and it must be stable. Okay, and last week we looked at consistency. How do we test whether a scheme is consistent? Well, you get your scheme, and you replace your U terms with Taylor series expansions. Okay, so if you've got U n plus 1, okay, you use the Taylor series expansion with respect to t, one step forward in time. If you've got ui plus 1, one step forward in space, and so on and so forth. Okay, and then once you've done that, once you've replaced your U terms with the Taylor series, you rearrange to get it in the form of the PDE which you're trying to solve, plus some higher order terms. If those higher order terms are of this form, okay, this form means they're of, if they're of order t and x, delta x. So this p and q will be some power. Okay, so this will give the behavior. If you have some other terms which aren't related to the Taylor series, then your scheme isn't consistent. Okay, so if you've got some other stuff in there which doesn't come from the Taylor series, once you've done all of this, okay, you can't say that it's of order delta t, delta x. You haven't got a consistent scheme. But if the higher order terms are in this form, then the scheme is said to be consistent and formal accuracy of pth order in time and qth order in space. Okay. And we looked at the first order upwind scheme, and we also looked at the forward time center space scheme. And I did put a scan of what we did last week on Moodle if you want to check it out. Okay. So that's the idea of consistency. So test for it, we just replace our U's with the Taylor series, rearrange to give the PDE plus some other terms. If your higher order terms are of big O notation, okay, you've got a consistent scheme. So that's half of it done. Okay, so we know how to do the consistency bit. Now we're going to move on to the stability. So is our scheme stable? Okay, so that's what we're going to be looking at today. Okay, and another thing I introduced the idea of last week was the Cfl condition. Cfl stands for Courant, Friedrich, Louis. Okay, a scheme must satisfy the Cfl condition. Did I look at this last week? Have you seen this before? Yeah, you have. Good. Sorry, I'm not quite with it today, really. Okay, so the Cfl condition, the fastest wave in our system, in our solution, cannot travel more than one node, spatial node, in a single step. Okay, so in order to capture motion, okay, it's got to be it can't pass through more than one node. Okay, so this gives us this criteria. Okay, so if v is our velocity, v times delta t over delta x, that has got to be less than or equal to 1. In other words, velocity times delta t is how far that wave has travelled over one time step. And if we multiply both sides by delta x, you can see delta x will be on the right-hand side. Okay, so we write it in this form, and we say that this is equal to c, which is known as the Courant number. So the Courant number is the velocity multiplied by delta t divided by delta x. That has got to be less than 1 to satisfy the Cfl condition. Okay. What we can also do is C in practice is set at a number that ensures that our scheme is stable. What we should say about the Courant number, the Cfl condition, that must be satisfied in order for a scheme to be stable. But just because it is satisfied doesn't mean the scheme is stable, if you know what I mean. It's a necessary criteria, but it isn't a complete one. Okay, so if you look at your CFL condition, you go, right, I've satisfied that. You could still have an unstable scheme, right? So this must be satisfied, but it doesn't. You can't just stop there. It doesn't mean it is stable. If we have a constant spatial step in our grid of delta x, then what we can do is we can calculate what we call the maximum allowable time step. This is the highest value of delta t for which our scheme remains stable. Okay, so quite simply, it's c, the current number, times delta x divided by the velocity. Now this is an important question. Okay, c has got to be less than 1, but we want c to be as high as possible, because when c is small, our delta t is going to be small, and we're going to use more time steps. So we want c to be as high as possible, but still remain stable for the scheme. Okay, so what we're going to be looking at today is how do we determine this value of c. Okay, and there are a couple of ways of doing it, and by far the most useful way is what's called von Neumann stability analysis. Now this uses something called Fourier analysis, Fourier series. Now I know not all of you have done it, Fourier series in the past, so for this intents and purposes, I'm going to brush over a lot of the theory behind this. And I think I've mentioned in the notes, but if you are interested in a bit more detail, at the bottom of page 52, I made a little note saying I've skipped over quite a bit of the theory. If you do want a bit more information, Hirsch is a very good book, and there I did a Google search earlier on. There's loads of sort of materials on this. Okay, so I am going to you've got to sort of trust me a bit on this. Okay, I'm not going to go into detail of the Fourier analysis. I'm just going to say, right, I'm using it. If you are doing is it digicoms and sound and image? Okay, you should be all over this. Okay, so von Neumann stability analysis. What we do is we're going to define an error. Okay, error, I'm going to use epsilon. So my epsilon is the error between the actual solution and our computed solution. Okay, so big U, actual solution, little u, computed solution. Sorry? That's not a power, that's a time step. So at each different time step, there's going to be a different error. Okay, and at each node, there's going to be a different error. Okay, so the sort of the superscript n is the time level n. Okay, what we're going to do is we're going to define g as the growth in error. So as we calculate and we march our schemes through time, okay, we don't want the errors to grow. Okay, there is going to be errors because we're only approximating it, but we don't want them to grow exponentially. Okay, so what I can say is the error at the next time step is equal to some number, g is just a number, multiplied by the error at the current time step. Now, simple rearrangement of this, I can calculate g by the error at the n+1 time step divided by the error at the nth time step. Okay, quite simple. For stability, we need that value of g to be less than 1. If g is greater than 1, what that means is the error at the next time step is grown. So the error at the time step after that is grown still. Okay, so eventually, after a few time steps, you've got errors are so big, your scheme is unstable. Okay, so we need our value of the amplification. Have I called it amplification here? But we tend to call this amplification. Okay, we need this to be less than 1. There's also quite a useful result. The error of a finite difference scheme will also satisfy that finite difference scheme. So, for example, last week we looked at the forward time-centered space scheme. Okay, and it's this here. Okay, I'll explain why I've used these subscript j's in a minute. Okay, so this is the forward time-centered space scheme. I've used c to replace v delta t over delta x. Okay. What we've also got is whatever error we have at the nth time level, the error at the nth plus 1, okay, also satisfies the scheme. So I could simply replace these u's here with the epsilons. Okay, so the errors also satisfy that. You may notice here I've used J as a subscript, whereas before, in the last week and last set of slides, I used I. Now, I've done this just for this von Neumann stability analysis because we use complex numbers. Okay, so I'm using I to denote the square root of -1. Okay, so in order to sort of avoid confusing between what's an index, so this will be an index I, and what's the complex number I just change the index to be J. Okay, so it's just a number. It means exactly the same as I, just to avoid any confusion. Okay, so what we want to do is we want to, using this, okay, we want to somehow establish what our amplification factor is. Okay, a couple of assumptions we have to make. Okay, these are assumptions we're making, but they're kind of safe assumptions. We assume that the PDE is linear. Okay, very few PDEs of any use are linear. The advection equation is linear. The shallow water equations, which we're going to be looking at in a few weeks, aren't linear. Okay, but for the von Neumann stability analysis, we assume it's linear, and we assume we have periodic solutions. Okay, so we can do that if we have periodic boundary conditions and they loop round. That's all well and good, but in practice, this, in theory, these should apply. It should be linear and it should have periodic solutions. In practice, it actually works, even if they're not. Okay, so you've got a bit of you've got the pure mathematicians sort of tearing their hair out at the numerical mathematicians here, because we just go, oh, whatever, it's gonna be fine anyway. So if you assume those two, but you've got linear and periodic solutions, then we can use Fourier analysis. Okay, what we do, and I'm missing out a large chunk of sort of explanation here, but it's sort of really outside the scope of the interest for this unit. If you are interested in this, by all means, have a search yourself. Okay, what we're going to do is we're going to replace our errors, the epsilons, with Fourier nodes. Okay, Fourier nodes are of this form, and this is something you just got to trust me on. Okay, so we have e to the at. Okay, a is just some number. Okay, t is our time. Okay, multiplied by e to the I. I is the square root of -1. It's our imaginary number. K subscript j. Now this is what we call a wave number. Okay, so if you've been doing digital sound and image, okay, you'll know about wave numbers. That's, for all intents and purposes, that is not really required for what we're going to do. But I've left it there just to be sort of more accurate, more precise. And here we've got x, and x is our space. So t is time, x is space, a is any number, I is square root of -1, k is our wave number. By the way, this kj, I've left it there, but we don't need it. Okay, I've just left it there for completeness. Okay, so that's what we say. We got the error at node j at time level n is equal to that. Okay, if you're doing Fourier series, you sum all those errors over the value of j, and you'll get some. You can convert it to some sines and cosines and sums of. Okay, that's a whole different course in itself, really. Okay, what if we've got the error at the next time step? Well, we take this, and the next time step is t, just simply t plus delta t. So here I've replaced t by t plus delta t. Okay. What have we got here? Well, here we've got the error at the node j plus 1, so that's one node to the right. Okay. So to get that, I've just replaced this x here in the top one by x plus delta x. Okay. And similar with the node to the left. So the j minus 1 node means x minus delta x. So I've replaced that x there with x minus delta x. Okay, so these are what we call Fourier nodes. Okay. So using this, all I do is I replace my epsilons, or actually even going further back, my u's. So this is my scheme, which full time center space scheme. I'm going to replace these. Okay, I've got the 4 of them here with those Fourier nodes, and we get this. Okay, that's a straightforward swap. It looks horrible, I know it does, but what we're going to do in a minute is simplify it all down. And what we want to find is we want to find for what value of exponential to delta t, okay, for what value is that less than or equal to 1. And I'll show you how we do that now. So this is the Neumann stability analysis. Okay, so this is for just that equation which I had on the previous slide. Okay, so this is the forward time center space scheme with replacing the nodes by the replacing the u values with the Fourier nodes. Okay, first thing I do is use the laws of exponents. I haven't written this in the notes because it's kind of a simple step, but all I've done here is laws of exponents. I've taken out the delta t, so I've got EA delta t there, and I've done the same with the delta x's. Okay, so hopefully you can see when you add powers, you just multiply bases together. Okay, so this is just getting rid of the brackets in the power there. Now what I've done is I've divided both sides by e to the at times e to the I kjx. Okay, so the left-hand side, if I replace that, if I divide that by essentially that, okay, I'm just left with e to the a delta t. Okay, that divided by itself, well, obviously it's just 1 minus c over 2. Okay, these first two e's here will just become 1 if I'm divided by itself. So I've got e to the I kj delta x. That's similar with this one here. Okay, so I've straight away applied laws of exponents, and then I've done some division throughout. So this doesn't look too bad now. It looks a lot sort of nicer than what we had before. Okay, I said earlier, but G was the amplification parameter, which was the error at the n+1 step divided by the error at the current step, n. Okay, so if I replace these with the nodes, Fourier nodes, okay, do a bit of dividing, we get that. Okay, which, as you can see, is the left-hand side of what I have here. So this is actually my G. This is my amplification factor. This is the growth in the error over one time step. I need to know for what value of C does this right-hand side less than or equal to 1. We've got a couple of problems here, though. We got complex numbers. Okay, I know you all hate them. We'll want to get rid of them. Okay, so, and we could use a nifty little trick. Oops, sorry, that was just saying what I said before. So e to the a delta t is the amplification factor from one step to the next. For stability, we need it, well, the absolute value of it, or the modulus of it, to be less than or equal to 1. In other words, the errors do not grow. How do we do that? We use trig identities. Okay, hopefully you've been familiar with these in the past. Do you know half angle formula, trig identities? Okay, so this is what we've got. Okay, I want to replace these exponents with sines and cosines. Okay, and one of the the sine trig identity, okay, is this: sine x is simply e to the ix minus e to the minus ix over 2i. Okay, that's just something you can look at. Probably something from, you see that in first year. I've seen these trig identities before. It's just a well-known trig identity. Okay, well, if you see up here, okay, we've got a similar form. If we say kj delta x is simply equal to x here, okay, I've got e to the ix minus e to the minus ix. Okay, the only thing I haven't got is over 2i. We've got over 2 there. The only thing I'm missing is I. So if I multiply top and bottom by I, okay, I could write this in this form. I have 1 minus IC sine, and then that in the bracket. By the way, that kj delta x in the bracket doesn't mean anything. Okay, in a minute, we just want to know how this sine function is going to behave. And remember, sine is a value between +1 and -1. Okay, so we need to know what are the sort of the limits of that sign value. Okay, so is that okay from that step? Okay, to that step there. So all I've done is replaced these exponents with this sine function, and I had to multiply top and bottom by I to get that 2i there. Okay, this is a modulus. Okay, modulus of a complex number. So remember, if I have a complex number of the form x plus iy, modulus is essentially Pythagoras' theorem. Okay, so multiply, you square the real part, square the complex part, add them together, square root it, you got the modulus. Okay, so I need the modulus of this. Okay, so if I square both sides, 1 squared is 1. Okay, on the left hand side, 1 squared is also 1. I squared by definition is -1, but then it's in front of a minus. That minus becomes a positive. C squared gives me C squared. Sine, whatever that is, gives me sine squared, whatever that is. Okay. So for stability, I've got to satisfy this condition. Okay. What you do here is you look at the behavior of your sine squared. Okay. So I mentioned sine is any value. Sine's got a value between 1 and -1. So if you square it, it's got a value between 0 and 1. Okay. So sine squared is greater than or equal to 0. Okay. It can never be negative. Okay. So this second term here, okay, that can never be negative. You're adding c squared times a number that can never be negative to 1. And you want to end up with a number which is less than or equal to 1. So the only time that can happen is when c equals 0. Okay. If c was, let's say c was -1. -1 squared is 1. 1 times a number which can only ever be positive plus 1 will give me a number greater than 1. Okay. So the only time that can happen is when c is equal to 0. That implies that delta t is equal to 0. Okay, so remember c is v times delta t over delta x. So if c equals 0, delta t is equal to 0. Okay, that means there is no value, no non-zero value for delta t for which the FTCS scheme is stable. So we say it's unconditionally unstable. Okay. In other words, it's rubbish. And we saw that last week. When I tried to use the FTCS scheme, it would just blow up. Okay. So this is the von Neumann stability analysis on it to say, okay, what's our maximum value of delta t we can use? Well, our maximum value of delta t is 0. So in other words, we can't use it. So that's the von Neumann stability analysis. It looks horrible when you first do it, but after a bit of practice, it's okay. Right, so we're going to look at an example again in a minute. This is the steps you take to do von Neumann stability. Okay, so you replace each instant of u in your finite difference scheme with the corresponding Fourier component. Okay, so it's some either that or some sort of slight change to that Fourier component. You've got to rearrange it, okay, to get g. So g, remember, is your e to the a delta t. You use this condition, okay, we've got to say, okay, modulus of g has got to be less than or equal to 1. G would be a complex number. Okay, so find out the modulus, square it, it'll be less than or equal to 1. Find out what values of c is your modulus of g less than or equal to 1. That can be tricky. Okay, that's a tricky stage. Sometimes you need to use trigonometric identities, usually sine and cosine. Sometimes you need to use vector norms. Okay, for all of the examples I'll be giving you, either now or perhaps if they appear in an exam, it's just replacing them with sines and cosines. Okay. If the modulus of g less than 1 cannot be satisfied for a positive value of delta t, the finite difference scheme is unconditionally unstable. Okay. If it can be satisfied, brilliant. You've got your maximum value of delta t. Okay. So I'm going to look at worked example is in your notes, but I thought I'd go over it, so you can see what steps I take. And just before I do, I'm just going to, so it's a first order at wind scheme. Okay, I'm just going to write it down before I switch to the visualizer. Okay, so okay, there's my old friend, the first order at wind scheme. Okay, there's your first order at wind scheme. So we're going to conduct a von Neumann stability analysis to see what value of that delta t is this stable for. So step one, first thing we do is we replace your u values with those Fourier nodes. Okay, I'm going to have to be very careful with my writing here. My writing is normally pretty poor, as you know, so I'm being extra careful with the detail of the writing here. Okay, so this is e to the at multiplied by e to the I kx. Okay, but instead of t, I've got t plus delta t because this is n plus 1 here. Okay, and if we do the same on this side, okay, I'm going to replace v dt over dx or v delta t over dx with c, just for simplicity, really. Okay, and then we have uj, that's e to the at multiplied by e to the I kjx minus e to the at multiplied by e to the I kjx minus delta x. Okay, so hopefully you can see where I'm using x minus delta x and why I'm using it there, because this is j minus 1 is the node to the left, okay, which is node x. If x is the current node, the node to the left is x minus delta x, which is why I put it there. Okay, next step, divide throughout by this term, okay, e to the at multiplied by e to the I kjx. So if I divide throughout, okay, I get e to the 8 delta t on the left. Okay, I get 1, just this term here divided by itself, minus c. Okay, again I'm going to get 1, so that's just that term there, minus e to the minus I kj delta x. I'll give you a couple of minutes just to sort of make it clear in your own head. Okay, so in this case, okay, I've got the minus delta x. Okay, so that's where that minus I, where that minus sign in front of the I comes from. Okay, and what we're actually doing here is following example 4.4.2, page 54. Right, so once you got down to this thing, remember your e to the at is simply g. Okay, we need to know for what value of c is this, the modulus of this, less than 1. Okay, unfortunately we have got an exponential function. Okay, exponential function will just disappear off. So I want to somehow replace this exponential function with sines or cosines. Okay, and I'm going to use a bit of a trick here. I'm just going to write down the, these are the trig identities, and I always forget them. Okay, so this is the one we used for the forward time-centered space scheme. Okay, so sine x is related to the exponential function ix. Do you know Euler's identity? Most beautiful equation in mathematics? That's where these sort of come from. Okay, so sine x, and we could also do the same for cos x. and cos x is e to the ix plus e to the minus ix over 2. Right, somehow I've got to fit these two into that. At the moment, it's not very obvious what I do. Okay, so I'm going to do a little bit of a trick. What I'm going to do is I'm going to split this in half. Okay, I'm not going to change its value. I'm not going to do anything strange to it. All I'm going to do is split this in half. Okay, so what I can say is G, sort of bypassing that, so to speak. Okay, I've got G is equal to 1 minus C, 1 minus, I'm going to divide this by a half. Okay, so if I divide that by a half, minus I kj delta x divided by 2. Okay, but I can't just halve it, so I've also got to have another half of it. So all I've done is split it in half. Okay, haven't changed the value. That's essentially saying, instead of saying 1 minus x, I've said 1 minus a half x minus a half x. Okay. So you can start to see, okay, why I did that, because both of these are sort of over a 2. Okay, what I'm also going to do is I'm going to add something to this bracket and also take it away. Okay, so remember, I'm not changing the value of it. I'm just adding something and I'm taking it away. Okay, so if I do that, so I've got 1 minus c, okay, minus e to the minus I k delta x over 2, e to the minus I kj delta x. My writing's starting to slip a bit. Okay, what I'm going to do here is I'm going to say, okay, I'm going to add an e to the ix. Okay, so e to the I kj delta x. Okay, the reason I've added that is because both of these identities have e to the ix in them, so I need to get that from somewhere. Okay, but I can't just add something because I've changed the value, so I've also got to take it away. So if I do that, if I take it away, so I've gone from this step here down to this step, okay, without doing really anything to it. I've not changed the value of this at all. I've just split this in half, added something to it, and I've also taken it away. Okay, right, so why did I do that? Well, I somehow wanted to replace the exponential functions with sines and cosines. So if we look at the sine x to start with, actually no, we'll look at cos x to start with. Okay, that one. Okay, I got e to the ix plus e to the minus ix over 2. Okay, so I've got to find that from here. So I've got e to the ix, which is that term there. Okay, that term there, plus e to the minus ix. Okay, so I could use any one of those two terms. So I'm going to use this first, well, that term with my left thumb finger and that term there. Okay, so that's going to give you minus cos kj delta x. Okay, so I've got rid of that one and that one. Okay, so it's a minus cosine, okay, and I'm using those two there. So that's the sort of towards the top of page 54 in the notes. Okay, so that's that done. I've still got these two here. But what we got here is instead of a plus, we've got a minus between them. Okay, so I've got a sine x, but the sine x is over 2i. Okay, so if I multiply these two, top and bottom, by I, okay, so we get plus I sine kj delta x. Oh, sorry, I minus sine. Yeah.
Why you don't do
Sorry?
Why you don't do
from what up here? Sine x squared plus.
You know, we found out I x is equal to cos x plus.
Yeah.
You're putting minus that one. It's literally
I'm quite glad you actually noticed that. The reason I'm doing it in this way is because when we do von Neumann stability analysis on a different finite difference scheme, you won't get it in this term form. You have to replace it with sines and cosines and do all this. You're right, for the first order Epworth scheme, we could have used the Euler equation on that. Okay, but if you were to do it for a different finite difference scheme, you wouldn't get this. You get another form. So I'm showing you the steps to go through. Okay, so very, very good observation. Okay, so right, we're down to here. Okay, and what I'm going to do here, I'm going to split this outside. Okay, I'm going to take it outside because what I want is G is a complex number. I want the real term of G and the imaginary term. Okay, so I have 1 minus C I minus cos kj delta x, just to make sure I've got the signs correct. Yep. Oh, I did have that right first time, sorry about that. Minus IC sine kj delta x. Okay, so those two terms here are my real terms. Okay, so if you think of a number in the form of x plus yi, oops, sorry, that's off the page a bit. If I've got a real number in the form x plus yi, my real term are these first two terms. Okay, my imaginary term is c sine kj delta x. Okay, what I want is I want the modulus of g to be less than 1. Okay, so what I want is 1 is greater than or equal to the modulus of all of this. Okay, so I should really sort of just make sure I've got my 1s not looking the same as the modulus sign. Okay, so I want this to be satisfied. Okay, get rid of the modulus, I square both sides. Okay, so I'm going to square both sides. 1 squared is 1. Okay, so 1 squared is 1. Okay, and here, the real part is 1 minus c, 1 minus cos k delta x. Okay, so that's the real part, and that's squared. Okay, I squared is minus 1, times by that minus is plus. So plus c squared sine squared kj delta x. Okay, so we've now got a lot of algebra ahead of us. Okay, so this is got one bracket in it. Okay, this is in the form a plus b all squared. Okay, so if we expand out this bracket, we'll have a squared plus 2ab plus b squared. Okay, so 1 squared is 1 plus 2ab, so plus 2 lots of minus c, 1 minus cos kj delta x. Okay, plus b squared. So I'm going to have c squared, and then the 1 minus cos kj delta x all squared. Okay, so that what I've just written down, that's just that square, the contents of that square bracket squared. And this c squared plus c squared sine squared x, that's the same. If you don't fancy writing this k delta x all the time, you can just replace it with x if you really want, because we're not going to. We don't really care what kj delta x is. That's just going to disappear later. But I've left it in there just for correctness. Okay, we've got to now square this. Okay, can you see this bracket here, the 1 minus cos all squared? So I've got to expand that out. So if I expand that out, everything else is the same. Okay, plus c squared. Okay, so I've got 1 minus 2 cos kj delta x plus cos squared kj delta x. And that's plus c squared sine squared kj delta x. Okay, so this is all in the middle of page 54. Right, what I'm going to do is I'm just going to flip over the page. So in order to not lose it, I've just frozen it. So I'm just going to write it out again. Bear with me. This sort of stuff's good for you. If you're wondering what, how the hell am I doing it all? You might need to sort of sit down tonight rather than going to the pub. You might want to sit down and try and follow this. I know it's good for you. Because right. Right, that's for crikey, so big we need to zoom out a bit. That's what we got. Here we've got a cos squared plus a sine squared. What's that equal to? 1. Right, so we can get rid of that. Ooh, that's a C. That's an open bracket. That's a C, by the way, in case you're getting confused by my writing. Squared. So if that's 1, 1 plus a 1 is 2. Okay. So I can start to sort of combine all this together. So I've got a 2c there, and I've got a c squared there, but I can take a common factor of 2 outside. So I've actually got 2c squared there. Okay, so what I can do is I can write this as 1 minus 2c, 1 minus cos kj delta x multiplied by 1 minus c. Okay. If we were to expand this out, you get that. Okay. So where did this come from? Okay, this is actually 2c squared, 1 minus cos. Okay, so I've got 2c squared there, and I've got 2c. So that's the 2c there, and that's my 2c squared. Okay. And if we subtract both sides, 1 from both sides, we get this. So, right, once we got down to, that's sort of as far as we can go in terms of simplification. Right, that's as far as we can go. We have to look at, okay, for what values of C is this negative? Okay, because we subtracted 1 from both sides. Well, cos 1 minus cos x, okay, is minus cos x greater than it. Yes, sorry, I was just confused there. 1 minus cos x is always going to be positive because the smallest value of cos x is minus 1. So 1 minus minus 1 is 2. And the largest value of cos x is plus 1. So 1 minus 1 is 0. So this function here ranges between 0 and 2. Okay, so if this is always positive and we need this to be negative, this 1 minus c must also be positive. So if this also has to be positive, so 1 minus c has to be positive, so therefore we can see c is less than 1. Okay. Remember, c is v delta t over delta x. Okay. Oops, sorry. If c is v delta t over delta x, this means delta t is less than or equal to delta x over v. So when I was doing the MATLAB program last week, I used 0.009. Okay, the smallest value I could have used was 0.01. Okay. We never actually go up to the highest value you could use because of this slight rounding errors in the computer. Okay, so we always go a bit less than that. Okay, that's for Neumann stability analysis. You're probably looking at that a bit shell-shocked. Okay, it takes a bit of practice, and it's not really there's a kind of set way of doing things, which is why I didn't go straight to the Euler equation. Okay, I could have gone straight to the Euler equation and cut out a lot of that working, but it wouldn't have worked for the other methods. Okay, so that was the example which ends on page 54. Okay, von Neumann stability. So for stability, you need to satisfy the Cfl condition. If that's not satisfied, you might as well give up. But if it is satisfied, you then have to look at von Neumann stability. What value of C is the modulus of G less than 1? Okay. What I'll be doing is if you want me to, I'll be scanning this in and putting it on Moodle as well. It's essentially just this page 54, but handwritten. So. Yeah. Yeah.
If we exchange V and C, it means, you know, T and X is the dependent variable.
Sorry, it's
T and X is the dependent variable.
Delta T and delta X are the steps, aren't they?
But when you do that one, it means theta X over theta V.
Yeah.
Is a slope of that one.
Well, delta T is just a step in the time. That's what you want to calculate. We want to know what's the maximum time step we can use. Yeah. So I mean, delta X is what you choose it to be. Depends on how many nodes you have in your finite difference mesh.
No, but in here show theta X over theta V should be bigger than the speed of that velocity of that leg.
Yes. Yeah. Yeah. So this is actually equivalent to the CFL condition. That's exactly. It's not always. For this particular example, it's the same as the CFL condition, but it's not always. Okay.
No, I mean, this condition should evolve and release this one new one.
Yeah.
Otherwise, that's one about this.
Yes, exactly. So, for example, what I'm going to do is just go back to. If I go back to the MATLAB. Okay, dt, if I set that to be slightly bigger, the highest value I could have dt in here would be 0.01. Okay, I set it slightly bigger. So if you dx is calculated. Dx depends on how many nodes we have. Okay. Yes, that's a good point. I'm going to do that in a minute, actually. Okay, so if I run that, it's slightly bigger. It's actually starting to go a bit. It's going a bit unstable. It'd be easier if I just sort of expand the axis a bit. Okay, you can see we're starting to get a bit of a growth there. Okay, if I was to allow that to carry on, that growth would just accumulate over time, and then eventually it'll become unstable. Yeah.
Why don't we have a square root?
Because you're square rooting 1. You've got to show that the modulus of G is less than or equal to 1. Yeah. Okay, so if we square root both sides, square root of 1 is 1. So we don't need it.
Yeah, but then when you work out the modulus of G,
but you're still, I mean, you're still looking at it for less than 1. So essentially, just to get rid of the modulus, you can just square both sides. You've still got that inequality. You're still testing against 1. Square root of 1 is 1. Yeah. So this is an example of using a. Okay, you can see there. At the moment, you might not think that's that bad. But we're also seeing a bit of oscillations in that there. Okay. What if I was to keep? What if I was to move the dt back to 0.009? Okay, but increase the number of nodes. Let's increase it to 200. So 0.009 was stable. I've increased the number of nodes to 200. Let's see what happens. Okay, boom, it's gone unstable. So because I've increased the number of nodes, I've decreased the spatial step. So the spatial step has decreased. So now the it's 0.005 is the maximum time step. So if I set it slightly smaller, i.e. 0.004, and I run it, and you can see it's stable. Okay, so if you do change your spatial step, you have to recalculate what's your maximum allowable time step.
if delta x and delta t is equal, what will happen here?
Depends what v is.
No, because you said delta t.
What I don't know what delta x is. What's delta x? So it's 1 divided by 200, 0.005. Yeah, in this case it is because v is 1. Right, so that's stability. Okay, and we've seen, so far we've seen we have a first order upwind scheme, which is, as you see, first order accurate. We have a forward time-centered space scheme, but we've just seen is actually unstable, so we can't use it. Okay. What we're going to do now is just have a look at a few more schemes. Okay. First scheme we're going to be looking at is Lax-Friedrich. So there's not a lot to these. Their derivation and their calculations are pretty much the same as what we've seen in the past, just with subtle differences. Okay.
Sorry, you know, this scale equation, they are not analytical solutions.
Yeah.
Why are they using this?
Not all equations have though.
Because their equation has analytical.
Yes. But what if we come up with a hyperbolic equation but doesn't have an analytical solution? How do we solve that? It's a good question. Why are we bothering with all this for the advection equation? Well, the reason we're bothering is any scheme which doesn't solve the advection equation won't solve a more complicated equation. So we're using this like a test. Okay. Right, so the Lax-Friedrich scheme, we've seen the forward time center space scheme is unstable. Okay, what the Lax-Friedrich does is attempts to stabilize it. Okay, so with the forward time center space scheme, you had a second order accurate approximation for the spatial derivative, but first order for the time derivative. So if we again use a second order central difference for the spatial derivative, backwards in time, but with the exception, the ui term in the time derivative is the average of the left and right neighboring nodes. So with the forward time center space scheme, this was just ui. Okay, with the Lax-Friedrich scheme, we replace it with the average of the left and right neighboring nodes. Okay, rearrange to make this as a subject gives you this scheme here. Okay, that's just that rearranged so that that term there is the subject, and that's called the Lax-Friedrich scheme. Okay. This Lax-Friedrich scheme is first order accurate in time, first order accurate in space. Hang on a sec. Didn't I just say I was using a central difference? A central difference is second order in space. Okay. So why is this only first order in space? That's a question on lab sheet 4, so I'm not going to tell you. Okay. So lab sheet 4, see that for that. So if you want to know what the formal accuracy is, you replace all these u's with the Taylor series, rearrange it to give you the PDE plus some higher order terms. And if you do that, you'll find that it's ordered delta t delta x. Okay. This is a stencil. Okay. So when we're calculating this node, we use these two nodes here. Okay. Notice we don't use that node. Okay. So when we're calculating the next node along, we don't use its previous value. We use the ones either side of it. And if I was to do von Neumann stability analysis for this, we can see that it's stable for when the current number is less than or equal to 1. And again, that's a question on the next lab sheet, so I'm not going to go through that one. Okay, so that's the solution. What I might do is actually, let's edit our MATLAB program to actually calculate the Lax-Friedrich solution as opposed to the first order upwind. Okay, so as you can see, I'm not changing any other bits of the code, just a half times the node to the left, node to the left, plus the node to the right, minus b times dt over dx, oh, 2dx, isn't it? So just remembering, yeah, b times dt over 2dx times the node to the right, minus the node to the left. Okay. Hopefully that's right. I'm just going to double check that. So all I've done is type this one in here. all the rest of the program exactly the same. So hopefully, fingers crossed, if I run it, it should work. There you go. And it's approximating that solution. You might start to notice, hang on, it's actually worse than the first order Atwood scheme. Okay, what we have here is we have dissipation. Okay, in attempting to stabilize the full-time center space scheme, the Friedrich scheme is introduced what we call numerical dissipation. It's smoothing out the Gaussian curve. If I was to run this forever, eventually it would just smooth out and just be flat. Okay, so that's the Friedrich's method. It attempted to do something and it just ended up making it worse. So we don't tend to use that one. Well, actually, we don't tend to use it for problems where we've got some sort of spiky profile. It is used elsewhere, though. Okay, then that's a Friedrich scheme. This is quite a nice one, Leapfrog. Okay, so what we do with the Leapfrog scheme is we use central differences for both time and space. Okay, so the time derivative, okay, we're replacing with central difference in space, in time, and the space derivative, a central difference in space. Okay, you rearrange this and you get this scheme. Okay, this is called the Leapfrog because if you notice in here, at no point do we use UIN. We don't use this node. The next value of this node here is actually calculated using the old values. Okay, this is the current values at time level n. The one before that is n-1. So we say it leapfrogs over the current value. So we use an old value from a previous time step to calculate the next value. Okay, so it's called the leapfrog scheme. But we do have a problem here. For the first iteration, what is our n-1? Okay, so when n is 1, when n is 0, n-1 will be -1. Okay, what do we start with? Okay, and the answer is we can use the forward time center space scheme. Okay, so the first value of the time step is unknown, so we can use the forward time center space scheme. But I just spent half hour showing you, but you can't because it's unstable. It's okay because we're only using it for one time step. Okay, in stable schemes, their errors grow the more you use them. If you just use them once, the errors haven't had a chance to grow. Okay, so what we do with the Leapfrog scheme is for the first step, okay, we use the forward time center space scheme, and for all other steps, we use the full Leapfrog. Okay, so using the full, so just saying what I just said, forward time center space scheme does not cause instabilities. Okay, so let's change our code. Actually, no, I won't change the code. It's going to sort of, you don't want to see me typing code all day. Okay, so this is the Leapfrog scheme. This is second order in time and space. So it's more, it should be more accurate than anything we've seen before. And as you can see, up here, it quite closely resembles our analytical solution. Okay, so it doesn't have the dissipation, but the first order schemes do. But what you might notice is that around about this area here, got little sort of wobbles, okay, little oscillations. Okay, that might be cause for concern, but for this problem, it seems to have worked all right. Okay, a better second order scheme is what's called the Lax-Wendroff scheme. Okay, this is a two-stage process, often called a predictor-corrector method. And this is, you got two types of predictor-corrector methods. Okay, ones you may have seen if you do Leader's multi-step methods unit. You have a predictor, and then you iterate the corrector until you get to some convergence. Okay, in this case, the corrector is only applied once. Okay, so you don't keep iterating the corrector. Okay, the first step is simply the Lax-Friedrich scheme, but it's applied over 1/2 time step and 1/2 space step. Okay, so what I've got here is I've got a blank stencil. So these are the current time values. That's your current IN value. So if I go 1/2 a step along in space and 1/2 a step up, Okay, what I want to do is I want to calculate the value of this node using the Friedrich scheme. Okay, so if I do that, okay, we get that. Okay, so what we have here is I have the value at the node, which is half a spatial step along and half a time step up. Okay, and that's simply the Friedrich scheme. And if I do the same for the left-hand half node, so instead of going up one in a half spatial step, I go down one in a half spatial step. Okay, so I can calculate these two from these three on the bottom. Okay, that's the first stage. That's what we call the predictor step. Okay, the second stage, which is the corrector step, applies the leapfrog scheme using this value here and these two. Okay, so if we pretend there was a node there, the leapfrog would go straight from this value over the top of it, leapfrog it. Okay, so it's a combination, the Latz-Wendroff scheme, of Friedrichs and the leapfrog. Okay, so this is over a full time step. So we have a full time step in this direction, and we have a full spatial step in the horizontal direction. Okay, so these are using these these are predictor values. So you see the n plus a half, we've already calculated those in the predictor step. The Latz-Wendroff is quite unusual for a predictor-corrector method. We can actually combine them just to write them as one equation. Okay, so if I combine the predictor and the corrector step, okay, there's my corrector step. And what I've done here is I've put in those Latz-Friedrichs schemes. So this one here is for the I plus a half, and this one down here is for I minus a half. Okay. Bit of algebra, okay, and we get that. So after a bit of algebra, we have something which resembles the forward time center space scheme. Okay, this first two terms here is forward time center space. But we have an additional sort of, it looks like a second order symmetric difference there. Okay, and so the actual stencil for the full Latz-Wendroff looks like this. Okay, yeah. So that's Latz-Wendroff scheme. Quite a nice little scheme. Second order in time, second order in space. And if you apply it, you get a pretty good result for your for the Gaussian curve. So we get very, very similar to the leapfrog, but we don't have those little oscillations in the tail of our curve. Okay, so that's the Latz-Wendroff. Yes, exactly. Leapfrog and this one are exactly the same. Now we'll come on to that. Yeah, this one's better. Leapfrog has got problems. I'll tell you in a minute. No, well, you got to wait. I don't want to spoil it for you. I said this is a, by the way, anecdote. I was in my second year graphics class yesterday, and they were all talking about Game of Thrones. And I said, if you don't do your work, I'm going to spoil it for you. And suddenly they all went, right, that's it. So I want to spoil it for you. I know you're eager to know. Right, the last scheme we're going to be looking at today. Okay, a bit of a sigh of relief there. This is Crank-Nicolson scheme. Now this is kind of a nice scheme. It's totally different from the previous ones, and I'll explain why in a minute. Okay, the Crank-Nicolson scheme uses a combination of the forward time centered space scheme and the backwards time centered space. Okay, the backwards time centered space scheme is exactly the same, except for we go backwards in time. Okay, so this is what we know. This is the forward time centered space scheme we know. The backwards time one, if you see here, we have n plus 1 values for the spatial step. Okay, and what Crank-Nicolson scheme does is we average the second terms in both of these equations. And if we do the algebra, we get this. Okay, so this is Crank-Nicolson scheme. It's an implicit scheme. All the ones I've done I've looked at up until now have been explicit. Okay, so what do I mean by implicit? Well, if you look on the right-hand side here, we have u superscript n plus 1. So we have n+1 values on the right-hand side. We don't know what those values are yet. So we have our next value of ui n+1 will be equal to some function with values which we don't know yet. Okay, so we could call this an implicit equation. Crank-Nicolson scheme is second order in time and space. Okay, so same order accuracy as Latch-Wendroth and the Leapfrog. It's implicit. If we have a look at this is the stencil. So this bottom sort of 3 nodes here, these are what we know. Okay, they're the current nodes. These top 3 are what we don't know. We're trying to solve for that one using nodes which we don't know the value of. Okay, so we can't do it using an explicit method. What's the great thing about the Crank-Nicolson scheme is unconditionally stable. It doesn't matter what value of delta t you use, it will be stable. Okay, so all the other ones, the explicit methods, there's some limit on the value of delta t. With the Crank-Nicolson scheme, there's no limit for stability. But that doesn't mean you should just whack in a great big value of delta t, because it's second order accurate. The larger your value of delta t, the less accurate your solution is going to be. So you've still got accuracy concerns there. Okay. How do we solve, or how do we calculate the solution using Crank-Nicolson? Okay, we've got a tridiagonal system. So this is the Crank-Nicolson scheme written out as the implicit equation. Just for simplicity, I'm going to let r equal v delta t over 4 delta x. And I'm going to move all of the n+1 values to the left-hand side. Okay, so all of the n+1 values to the left-hand side, and I get this. Okay. We know the right-hand side values because they've all got superscripts n. We don't know what the left-hand values are. So what we have is we have a linear system. Okay, so I've written it in the form of a matrix equation, similar to what we had with the elliptic Laplace's equation. So here we have our linear system, and we can solve this tridiagonal linear system using the Thomas algorithm, which we looked at when we looked at elliptic equations. So that's I'm not going to show you the MATLAB. If you want to do it yourself, you can. But that's the Crank-Nicolson scheme. So you solve for a whole row of nodes at once using the Thomas algorithm. Okay, so that's the Crank-Nicolson. And if I apply it to the Gaussian curve problem, that's the solution. Not quite as good as the Leapfrog or the Latch-Wendroth. Okay, a couple of things to note. We've got a little sort of a dent here, got a little bit of what we call an undershoot. Okay, so there's a little undershoot towards the tail of our curve. And what that's caused is a little bit of a phase error. We're a bit out of time here with our curve here. So we haven't got quite, it's not a brilliant solution. Okay, it's very stable, unconditionally stable. It doesn't matter what value of delta t we use, it's always stable. For this purpose, I use the same value of delta t as I did for all the other equations, or the other schemes, just for fair comparison. Okay, so how many schemes we've got? We looked at first order at wind, forward time center space, which is useless, Latch Friedrichs, which tends to be too dissipative, Leapfrog, Latch-Wendroth, and Crank-Nicolson. But that's not an exhaustive list. There are plenty of schemes out there. You just choose different finite difference approximations, insert them into the equation, excuse me, insert them into the equation, derive your schemes, check for them for consistency, check for stability. If that's all good, you're good to go, and then you can test them. And you test them. If they're rubbish on solving this type of problem, they're going to be rubbish solving a more complicated problem. Okay. Coming back to your question about what's best, Leapfrog or Latch-Wendroth, and why. This problem with the Gaussian curve is quite a smooth gradient. Okay, so as the gradient goes up here, it's all very smooth. There's no abrupt changes in the profile. I mentioned last week hyperbolic equations. They can model discontinuities. So what I've done is I've used what we call a top hat test. And here, the initial profile has a couple of discontinuities in. So the initial profile goes along and straight away it jumps straight up to 1. Okay, so this should have a gradient of a very, very large gradient. It's actually a Fisher's gradient of infinity, but obviously we're approximating it with a mesh. So this got a sudden abrupt change, it has a very large gradient, positive gradient up here, flat, and then a very small or very large absolute value negative gradient down here. Okay, so this is what we call a top hat test case, because it looks like a top hat. Okay, and what I've done is I'm applying each of these schemes to this problem. Actually, the first order upwind scheme seems to approximate it quite well, hasn't performed badly. Okay, you wait until you see some of the others. We do have a bit of a problem here. We've got a bit of a smoothing out. Okay, so it hasn't sort of kept this region on this region down here as well. So we've got a bit of a smoothing out. If I was to continue this forever, or say forever for longer, what you'd find is you'd find dissipation. It'll come in and your top hat function, which should look like that, will just start to smooth and it will eventually just disappear. Okay, so it may look good, but after a while, if I was allowed to continue, it'll just sort of smooth out. Friedrich's pretty poor. Okay, another first order scheme. A feature of Friedrich's is you can get these sort of jaggedy, sort of where two nodes sort of pair together. They either look like jaggedy or they start to oscillate a bit. It's actually Friedrich's. It's even worse than the first order upwind scheme. So that was the one you started with. This was meant to be an improvement, and it's pretty rubbish, so we don't tend to use it. Okay, there's the Leapfrog scheme. So something has gone a bit wrong there. Okay, Leapfrog scheme looked all right when we did it with the Gaussian curve. As soon as we give it a sort of steep gradient to model, okay, doesn't like it. Okay, massive oscillations, and you could probably guess we don't use that one for this problem. Okay, Lax-Wendroft, much better. Okay, still not ideal, but a couple of things I want you to notice about this. Okay. We've got much less dissipation around this region than the first order schemes. Okay, if I just go back to the upwind scheme, there you have. You look at that dissipation there. After a few more time steps, that will become increased. With the Lax-Wendroft, that will stay like that for forever. Okay. We do have an overshoot here, bit of an overshoot, bit of a bump, and we have an undershoot in the tail of the top hat. Okay, Gibbs phenomenon. You know, you guys are doing sound and image processing, that sort of idea of Gibbs phenomenon. That's a Lax-Wendroft scheme. We don't have those oscillations that the Leapfrog scheme had. Okay, so Leapfrog scheme, pretty rubbish. Lax-Wendroft scheme doesn't suffer from that. Unfortunately, the Crank-Nicolson scheme does suffer. Okay, this one is oscillatory. Where do these oscillations come from? They actually come from the second order approximation of the first order derivative. Okay, so the reason why our first order schemes didn't have these oscillations in because they were first order. Second order schemes had these oscillations in. Okay. So what we can do is we can use the Lax-Wendroft scheme, but only use a first order scheme around where these little oscillations are going to occur. Okay, and that's called a TVD method. If you want to know about that, I'll let you ask Alex. Where is he? Alex here? Yeah, do you want to talk about that? Didn't think you would. No. Okay, so we can improve on these schemes. Right, so that's hyperbolic PDEs. One thing I would say about them is I've shown you lots of schemes and I've shown you lots of stuff which doesn't work. Okay, these might work in other cases. They just happen not to be very good at the hyperbolic PDE. They might be fine at a parabolic PDE. And in fact, when we look at the heat diffusion equation, we'll use the forward time center space scheme. But for this hyperbolic PDE, they're rubbish. Okay. Right, before you decide to disappear, anybody not submitted their report for lab sheet 3?
Excuse me, like the
Oh, sorry. I'm just going to turn off the screencast. Yeah.